Thanks everyone. This is your review video for Unit 1, Measurements and Matter. And I'm going to try to create review videos for each of the units. This is just to help you get a handle on everything that is covered in the unit and to review some important concepts and give you a few extra practice problems and a few pointers to help you do well in the test. I'll try to make these as brief and concise as possible because you have a lot of resources at your disposal, including, of course, your notes and the PowerPoints and lots of practice problems on the website. So this is just kind of a final review that will help sort of tie everything together. So you may remember that our unit began by talking about the nature of science and how we know what we know and the difference between theories and laws. And I want to just remind folks that this is not an intuitive concept. So you have to really fight your intuition on this. For example, your intuition may tell you that theories are uncertain, laws are certain, for example, but you have to fight that because they're completely different things. So one of the most important things to understand is that laws and theories are fundamentally different. Laws come from observations. If we see something again and again and again in nature, we see a pattern, we summarize that pattern in a natural law. Now remember that once laws are established, they're pretty certain in the sense that we don't expect and haven't really seen examples of patterns just sort of changing willy-nilly. However, we do have loopholes in laws. We can study these phenomena under new conditions, and they may not behave in the same way that they did under the original conditions. So laws do have loopholes, and laws can be expanded and revised. As we've said, nothing in science is 100% certain. You can't prove anything 100%, but you can gather a lot of evidence and be relatively certain that things are true. So there are these patterns in nature, and remember, these typically come first. And then afterwards, we come up with some inferences based on our observations, and with a lot of evidence and a lot of testing, these inferences can eventually become theories, which are well-tested explanations for the patterns that we see in nature. And these theories have a lot of evidence to support them. Remember, though, that theories, first of all, cannot be proven correct because there's always the possibility that one day we'll discover new information that would cast doubt on the theory. And remember, too, that theories can be proven wrong. If we come up with new evidence that contradicts a theory, then theories need to be revised or thrown out. One common question is, can a theory become a law? And the answer is, of course, no, because theories are explanations, laws are patterns, and an explanation cannot become a pattern. So this is a very important framework, which we'll come back to again and again as we progress through chemistry, because there are many laws and many theories we're going to study this year, but we want to always come back to this framework to understand the nature of the kind of knowledge that we have in science. So these are the prefix conversions, and if you recall, there is a mnemonic for these, and I'll just start up top. So it is: my kitten, base unit, didn't comfort my moody neighbor. Now you have to remember where the base unit is, and you have to remember that moody is micro here. Remember also that between each of these there are 3 powers of 10. So 3 powers of 10, 3 powers of 10. However, between the base unit and decicentimilli, there's just 1 power of 10. So 1, 1, 1, and then 3 powers of 10, 3 powers of 10. Remember, as the unit gets smaller, the number gets bigger, right? So the two move in opposite directions. And normally we see this instead of vertically, we see it left to right with mega on the left and nano on the right. And that's a convenient way to show this, because if you're moving to the right, that means you move the decimal to the right and the number gets bigger. If you're moving to the left, you move the decimal to the left and the number gets smaller as the unit gets bigger. Again, those move in opposite directions. So as we're going to the left, right, mega's on the left of the line, we move the decimal left. As we go towards nano, we move the decimal to the right and the number gets bigger. By the way, I shared with you some additional practice problems, which includes unit conversions. If you're having trouble with unit conversions, I strongly encourage you to do those practice problems and check the answers. And here's a practice problem that I'd like you to try to see if you understand this. So what I'd recommend is you pause the video right now, do this practice problem, then hit play and see if you get it right. Okay, hopefully you've done this problem, and hopefully you got 4.6 times 10 to the third nanoliters. So we're going from milli to nano, so that's going in the right direction. Nano is a very small unit, so the number is going to get bigger, so recognize that at first. And we're moving 6 powers of 10 to the right. So since this is a number in scientific notation, basically what I can do is I can just multiply the whole thing times 10 to the 6th. So 4.6 times 10 to the minus 3 times 10 to the 6th. When you're multiplying with exponents, add them. So that's 10 to the third. So that's how I got 4.6 times 10 to the third. Of course, it would be perfectly acceptable to express your answer as 4,600, which is the same thing as 4.6 times 10 to the third. And it has the same number of significant figures as well. So unless you're requested to put the answer in scientific notation, feel free to write it however you wish. Okay, here's another practice problem. 1,200 kilograms equals how many centigrams? Again, I would encourage you to pause the video now, try it, and then hit play again. Okay, you've tried this problem, and I hope that you got 1.2 times 10 to the 8th. Remember, we're going from a big unit to a small unit, and so the number is going to get bigger. And so the way you might do this, kilo to centi. So kilo to the base unit is 10 to the third, and then centi is 2 more, so that we need to move 10 to the 5th. So the way I would do it is I'd just write 1,200 times 10 to the 5th, and then I know I need to convert that into scientific notation. So I know I have my decimal point here, and I need to move it over 1, 2, 3. And as I make this number smaller, I need to make my power of 10 bigger. And so instead of 1,200 times 10 to the 5th, it's going to be 1.2 times 10 to the 8th. Remember, I have to drop these 2 zeros because they're not significant. All right, final practice problem, 645 micrometers equals how many megameters? Again, I would encourage you to pause it and try it. Okay, you've tried this, and I hope that you recognize we're going left on the number line this time, which means that I'm going to get a very small number because the unit's getting very large. The answer is 6.45 times 10 to the minus 10. So if I'm going from micro to mega, okay, so micro to milli is 10 to the minus, it's going 10 back, so 10 to the minus 3. Milli to the base unit is another 3 back, so now we're at 10 to the minus 6. 3 more back. 10 to the minus 9 is kilo, and then 3 more back, 10 to the minus 12 is mega. So I could write the answers first, 645 times 10 to the minus 12. I can't leave it like that. That's not a valid way to write a number. So I could, put a decimal and a lot of zeros, but this is definitely one you'd want to put in scientific notation. So 645 times 10 to the minus 12. My decimal's here. I move it over 2 places. I'm making this number smaller, so I need to make the other number bigger by 10 to the second. And so I'm basically going to say 10 to the minus 12 times 10 to the second is 10 to the minus 10. I'm adding my exponents. 645 times 10 to the minus 10. If you're still having trouble on this, there are you'll see linked to the topics page a worksheet with lots of practice questions and answers. So I'd encourage you to really work on that. And if you're still not getting them right, then feel free to come see me for some extra help if there's still time before the test. Okay, with respect to measuring, remember we always reach the first uncertain digit. That rule is never violated, meaning that if there's a mark on the device that you are using, it's certain because you can see whether it's before or after that mark. What you're estimating is between the marks, right? So in this case, the 2 is certain, the tenths place is certain because it's marked, and the 2 is an estimated number. And remember, reasonable people can disagree on what that estimate is, right? It's uncertain. Remember, if you're using an electronic instrument, the instrument already is estimating the last digit. So all of the digits given to you are significant. The last significant figure is always the uncertain digit, but there's always uncertainty in every measurement. So really make sure that you understand this. Our measurement activity was a good test of kind of how to read various instruments, and certainly on the test you'll see some questions where you're measuring the, let's say, volume of a liquid in a graduated cylinder or the length of an object with a ruler, and you just have to make sure you always estimate one digit. Don't forget units as well, very important. Okay, the difference between accuracy and precision, we can summarize by saying accurate means correct, precise means consistent or exact. And again, for this, you're going to have to fight your intuition a little bit, because we tend to want to use the word accuracy in place of precision, right? But precision, they're really two totally different things, completely unrelated. Accurate is correct. Precision means how many significant figures you have. So it is possible for a measurement to be both precise and accurate, and that's what we want, right? We want the measurement to be very exact, to have as much information and as little uncertainty as possible, and we also want it to be accurate, right? So a very sophisticated balance that's well calibrated would, for example, give you a measurement that's both precise and accurate. But you could have a measurement that is precise but not accurate. So this is a very exact measurement that is off from the real value. So an example of this is a very sophisticated balance which has been damaged perhaps, and the calibration is now off. So you're getting a lot of significant figures, but they aren't accurate numbers. When is a measurement accurate but not precise? So this is when we're using a more crude instrument or a cheaper instrument, which gives an accurate number, but there's still a lot of uncertainty, right? So we might measure the mass of a pencil on a balance that only reads the tenths place. If it's well calibrated, it's going to give us an accurate answer, but an answer that's imprecise. And we have still a lot of uncertainty about the exact mass of that object. So really make sure you understand the difference between these two things, and that you could explain the difference. Okay, significant figures, the reason we use them is to keep track of precision in our measurements, right? So is there a difference between 4 and 4.000? Absolutely. The 4.000 was measured with a much more sophisticated instrument. The uncertainty is in the thousandths place, whereas in the number 4, the uncertainty is in the ones place. Huge amount of uncertainty, right? They both might be accurate, but one is far more precise than the other. So we have certain rules which tell us how to count significant figures. And I think the simplest way to express these rules is the present-absent system. If you see a decimal point, if a decimal point is in the number, it's present, you have to remember to start counting left to right, because P points right. If the decimal point is absent, there's no decimal point, you start counting right to left. The way you remember that is A points left. Okay, so 2 sample problems here. 22,000. Again, you may want to pause the video just to do the quick count. Hopefully you don't need to pause it because it's a quick calculation. And I hope that you recognize here a decimal point is absent. So I'm going to start counting right to left with my first non-zero digit. And that means only those 2s are significant and the 0s are not significant. So remember, if I were to convert this number to scientific notation, I would be dropping those zeros, right? So 1, 2, 3, 4, I'd be writing 2.2 times 10 to the 4th, no zeros. In the number below, a decimal point is present, right? So I hope that you would know we'd start counting the other way, left to right. And again, once I get to a digit, once I start counting, I can't stop. So I start with my first non-zero digit, which is a 2, and I count those other zeros, 3 significant figures. All right. I think based on your performance so far, you're pretty good with counting sig figs, but it would be helpful just to review the rules. Remember that any number that's exact has an unlimited number of sig figs. So that includes counting numbers. So anytime we're counting objects, for example, there's no uncertainty in that measurement because I know exactly how many objects there are. So, for example, 12 students is 12.00000 to infinity. Exact numbers have an infinite number of significant figures. Also exact conversions, right? For example, 1 meter is exactly 100 centimeters, so it's 100.00000. So if you have these exact conversions or counting numbers in your calculations, do not let them limit the number of significant figures because they have an unlimited number of significant figures. And then the general rule applies only round at the very end, but this rule only applies if the operations you're doing follow the same rule. So for example, if you're just doing multiplication and division, keep your numbers until the very end, then round to the number with the least sig figs. However, if you're doing some intermediate calculations, for example, if you need to calculate the density of an object with displacement of water, then you have to do two things, right? First, you have to subtract the two volumes in the graduated cylinder, and then you have to divide mass by that volume. Okay, so whenever you're doing two different types of operations, then you have to follow the rule within each calculation. So for that subtraction, I'd need to follow my addition-subtraction rule, and then I would, with the number of sig figs that I got from that, follow the multiplication-division rule. So again, the rule is you take the, if you're multiplying or dividing, you have the fewest number of sig figs in either factor. That's what you're going to put in your answer. So we saw this example in class. With 4 sig figs, 3 sig figs, I'm going to round to 3 sig figs, 324. Just a common mistake that people make, and I want to just alert you to it here, is if, let's just assume, okay, this was not significant, and this had 2 sig figs. If I still got this as my answer, and I had to round it to 2 sig figs, I'd need to round to this place value, okay? Some people would write then 32. Okay, that would be very wrong because this answer is nowhere near 32. So if I'm rounding to this digit, I need to put a 0 here as a placeholder, right, to keep the value of the number the same. Okay, so the correct answer, if this were 2 sig figs, would be 320. Okay, I just wanted to point that out because it's a common mistake, and I've seen it again and again. So if you're rounding to the ones place as you are here, that's pretty straightforward. But if you're rounding to the tens or the hundreds place, just remember not to change the value of the number. When you're adding and subtracting, the rule is the place value at the greatest uncertainty determines the place of the last sig fig in the answer. So if I'm adding 3.75 to 4.1, my uncertainty is in the hundreds place in the first number, the tenths place in the second number, and so I'm going to round to the tenths place. Our rule is if the next digit is 5 or higher, you round up. If it's 4 or lower, you round down. Here, in the top number, I have uncertainty in the ones place. In the bottom number, I have uncertainty in the tens place. So I have to round to the tens place. And this is an example where I need that 0 as a placeholder to get the correct answer. So these practice problems we saw in class, multiplying and dividing, 4 sig figs, 2 sig figs. I'm going to round my answer to 2 sig figs, of course. In number 6, I'm subtracting. I have uncertainty in the tenths place in the first number and the hundreds place in the second number. So the tenths is a greater uncertainty. I'm going to round to the tenths. Scientific notation I've already kind of alluded to earlier, but to put a number in scientific notation, we first need a number between 1 and 10. And then remember, if you make the original number bigger, you need to compensate with a negative exponent. If you make the original number smaller, you need to compensate with a positive exponent. Okay, so in this case, I'm moving my decimal place from the third 0 4 places over. So 1, 2, 3, 4. That gives me 6.5. These zeros are not significant, so I drop them. And I made this number smaller, so I need to compensate with a positive exponent. Only includes sig figs. So we did these practice problems in class, but just as a reminder, these zeros are not going to be significant. I need to move the decimal over 6 places. So I'm making that number smaller. I need to then compensate with a positive exponent. In number 8, I'm moving the decimal to the right. I'm making the number bigger. So I need to compensate with a negative exponent. And remember that 0 is significant, right? Because it falls after the decimal point. So I need to keep it. I should also be able to convert from a regular number back from scientific notation back into a regular number. So all I do is move the decimal the appropriate number of places. So if I have, for example, 7 times 10 to the minus 5, my decimal's here. I'm going to move it 5 places to the left, giving me 0.00007. And if I have a positive exponent, as I do in number 10, I'm going to move the decimal, in this case, 4 places to the right. And that gives me 62,000. Those zeros not significant. And in doing calculations with scientific notation, I hope you've had enough practice with this to know how to do it on your calculator. Use the EE key, okay? I cannot emphasize that enough. If you try to do times 10 caret 7, right, you will likely make a mistake. When you're using the E key, you do not need parentheses, you do not need times, you do not need a caret, you do not need a 10, right? So to type this number, I'm just going to type 5.44 E7 divided by 8.1 E4, and that should give me my answer, which I then know I need to round to 2 sig figs, which would be 670, not 67, right? Okay. That's how I would express it in scientific notation if I wanted to. All right, classification of matter. This was kind of the second part of the unit. Remember that matter exists in two types of substances. You can have pure substances or you can have mixtures. A pure substance is either an element or a compound, right? And the thing that distinguishes a pure substance is that it always has the same set of chemical and physical properties, right? No matter the amount. Whereas impure substances, depending on the relative amounts of each substance in the mixture, the chemical and physical properties will change. So just remember, for an element, we know it's an element if we find it on the periodic table. It's a compound if it's a chemical combination of two or more elements. For mixtures, there are two types of mixtures. One is a homogeneous mixture, meaning you cannot see the different parts of the mixture. And then a heterogeneous mixture is you can visibly see the different parts of the mixture. So these are pure substances, and if a compound just consists of one type of element, you probably have heard of O2, for example, or N2. These are two gases that are in the air. Most of the air is either nitrogen or oxygen. And even though there's a 2 there, it's still an element because there's only one type of element in the molecule here. Whereas these are compounds because there are two or more different elements: carbon dioxide, nitrogen dioxide, water, nitrogen oxide. These are all compounds, but everything on this slide is a pure substance. This is a really useful slide, and I would really encourage you to study it and understand it. So if we see just one thing, one element here, then clearly it's a pure substance, and clearly it's an element. This is also an element, right? Because these two atoms are the same element, right? So that it's true that they're molecules, but it's still just an element. It's not a compound. Okay. Here you have a compound because you have molecules, right, which consists of, in this case, two different elements, right? This is actually probably ammonia or maybe nitrogen trioxide, something like that. And here's a mixture, right, where we have all sorts of different compounds and elements mixed together. So make sure you understand the difference between mixtures and pure substances at the molecular level, and make sure you could identify those. So finally, we talked about how you might separate different mixtures, and distillation is a great tool to separate a homogeneous mixture. If you have a homogeneous mixture of a solid and a liquid, for example, salt and water, then you can use a process called crystallization. You could also use distillation. Really what you're doing is you're boiling off the water, leaving behind the solid salt or whatever solute is in there. Specifically, though, distillation is appropriate for a mixture that is homogeneous but consists of two liquids that have different boiling points. So we take advantage of the different boiling points, right? And this is showing salt water, but really better to use distillation for something like a mixture between alcohol and water. And you'd basically start boiling the mixture, and the substance, the liquid with the lower boiling point, would boil off first. It gets passed through this tube here, which has cold water running through it, and that condenses the liquid, and so then it drips into the receiving flask. And so at the end of the procedure, you have one liquid here and the other liquid here, which hasn't yet boiled off. So that's for homogeneous mixtures of either a solid and a liquid or two liquids. If it's a heterogeneous mixture, you're going to want to use a process called filtration. So basically, you're going to pour the mixture through a filter paper, and the water drips through, but the solid insoluble salt or substance, could use this for sand as well, does not go through. It gets caught in the filter. Right, so that's a great way to separate a heterogeneous mixture. And then finally, electrolysis is used not to separate a mixture, but actually to separate a compound. So we can actually pass electricity through a compound like water and separate it into its individual elements, hydrogen gas and oxygen gas. So no, these previous separation techniques were physical changes, right? There's no chemistry going on in either of these. However, electrolysis is an example of a chemical change, chemical separation. And the last thing is just states of matter, solid, liquid, gas. So make sure you kind of have a vision for what this looks like at the atomic molecular level. And the way we can go from one phase to the other is with heat, right? So as I apply heat, I go from a solid, then I melt it to turn into a liquid, and then eventually I vaporize it to turn it into a gas. And if I go back, this is called condensation, and this is called freezing. I can also skip over the liquid phase entirely and go from a solid straight to a gas, and that's called sublimation. Or I can go straight from a gas back to a solid, and that's called deposition. So another way, actually, we can go between the phases is by changing the pressure. As you decrease pressure on a solid or liquid, it tends to turn into a gas. Whereas just likewise, if I increase pressure on a gas, it will liquefy or solidify. Okay, I'm just looking at I just went over the test and I kind of made some notes about things that are on the test. And this follows very closely the review sheet that I gave you. So states of matter, properties and terms, uncertainty, measuring, molecular level diagrams, theories and laws. Oh, absolute zero. We haven't talked about that, but it's in your notes. So make sure you review absolute zero. And the Kelvin scale, of course. And by the way, we use that, of course, to just have a scale with no negative numbers. Absolute zero is the point, the lowest possible temperature, all matter stops moving. And you can't go any lower than that. The other thing that wasn't on this slideshow was types of errors, including systematic and random errors. Remember, a systematic error is a mistake in the procedure, or it's human error. And importantly, it is something that can be corrected for. It's something that we can fix if we do the experiment again. We identify the error and we do the experiment again without the mistake in the procedure. The other type of error is a random error. Random errors are present anytime you make a measurement. You cannot eliminate random errors in the lab. However, one way to mitigate the effect of random errors is to do the experiment multiple times. That is, do multiple trials. Because these random errors, because they're random, they tend to be above the actual value just as often as they are below the actual value. And so if you take an average, the extremes tend to cancel out, and you tend to really hone in on the correct value that you're after. Physical and chemical changes, got that, adding, subtracting, multiplying, dividing with significant figures, being able to calculate density, right? So making sure you know the formula for density and making sure you know how to do a calculation where you calculate density by displacement of water, just like you did in the measurement activity. Accuracy and precision, scientific notation, unit conversions. Okay, there's Kelvin. And that's pretty much it. So the test is going to be maybe about 20 multiple choice questions, and then the rest would just be calculations and in short answer. So if you've done your practice, done your preparation, I think that you'll find the test very reasonable and you should do well. Like any good test, it is designed to measure what you know If you have mastered this material at a high level, your score will reflect that. But on the other side of that is if there are weaknesses in your mastery, the test is designed to identify those and pull those out and measure those weaknesses. So if you don't know the material very well, then you probably won't do very well on the test. That's how the test. That's how any good test should be designed, right? To measure